Everyone, my name is Nicole. My mentors are Mike and Zubin. And I work for Professor Michael Doherty on this project named Polymorph Transformation of Clopidogrel Hydrogen Sulfate. So let me give you a little bit background on polymorphs. Polymorphs are the same chemical compounds that have different crystal structures. An example would be diamond and graphite, which are not completely, but they're very different from each other. They have different properties, as you can see right here. And another example that really I want to focus on to talk about to stress how important polymorphs are is this drug called ritonavir. It was an AIDS drug that they had in 1996 that they produced. ABBA produced, and so what happened was that they had only one polymorph formed when they first produced it, and two years later, or roughly 2 years later, they found out that the form of crystals is not really working. So they took it back to the lab and looked at it and realized that there's another form of crystals that's formed in this drug instead of the first one that they wanted to use. So this form 2 polymorph, or whatever form it was, that it actually had a dissolution rate that is only half of the dissolution rate of the first one, and it also had a different shelf life. So ABBA spent, just to try to change form 2 back to form 1, they spent $250 million on it, and they lost on a magnitude of some billions of dollars on this drug that they knew nothing about. They knew a lot about it, but not the polymorphs. So basically what I'm trying to tell you guys is that polymorphs are very important and worth looking at. And the drug that I'm working on right now is called clopidogrel hydrogen sulfate, which is short for CHS. It is an active ingredient in Plavix. It's a blood thinner. It has 2 polymorphs that are known, and for my project I want to understand the nature of shift and regeneration of a form. So let's talk about project goals. The first thing that I looked at was solubility, which is for a specific concentration, what saturation temperature I would have that at that temperature where I can actually form crystals. And then afterwards I looked at the metastable zone width, which is from the saturation temperature where you form crystals to when the crystals will spontaneously nucleate, which means that you don't need any seed crystals. They would just form by themselves. And then afterwards, I looked at polymorph transformation, which is how it transforms from form 1 to form 2, or whatever forms that they would have. So in order to look at the solubility of polymorphs, we have to first look at, what kind of polymorphs that I have. So I have form 1, which is metastable, which is the metastable form, and form 2, which is the thermodynamically stable form. So theoretically speaking, it was somehow transform from form 1, and then it would go to form 2. And in order to look for the solubility, I use this temperature measurement, which is the polythermal method, which is starting from whatever my powdered crystals are from, or powdered compounds, the temperature is, and I raise the temperature up to something that is above the saturated temperature. And so I wait till all of the powder has dissolved, and then I plummet the temperature down to something that's way below the metastable zone temperature, which is just some hypothetical temperature, and then I would see crystals spontaneously nucleate. And then for these crystals, they were really tiny right now, so then I can just dissolve them. So I hold that until it reaches equilibrium, and then I raise it back up to right underneath the saturated temperature, and then I wait for it to reach equilibrium again, and then I increase the temperature by approximately 1 Kelvin per hour until all of the crystals have dissolved, and I can therefore say that this is my saturation temperature. So this is the data that I got from my solubility values. It's just an exponential fit, and that from thermodynamics, I know that at equilibrium I would have this relation of solubility and temperature, and assuming that the activity coefficient is 1, which is an ideal solution, that therefore I can just say that the ln of my solubility is proportional to inverse of temperature. So therefore I can just grab it as a straight line and say, oh, ln of x is y-axis, and then inverse of temperature is right here. So then afterwards I looked at the metastable zone width, which is basically having the temperature of the crystal solution that is above the saturation temperature, and then I plummeted it so it can like start forming crystals and look at the induction time. And for whatever induction time, inverse induction time equal to 0, that means the induction time is, infinity. That means no crystals would just spontaneously nucleate. I would therefore know what kind of undercooling or temperature change would give me a kind of crystals that would not spontaneously nucleate, which is basically the definition of what metastable zone width is. So for my compound, no nucleation was observed, even though I have left them alone for like an undercooling of 45 Kelvin over a long time that I was looking at it. So then they basically concluded that my metastable zone width is not going to interrupt or interfere with any of the experiments that I'm going to work on for my polymorph transformation experiments. So with that, let's talk about polymorph transformation. I used a Peltier cell for it because it gives you a really accurate change in temperature. And so first I prepared my seed crystals and solutions in water baths, and then I observed them underneath the microscope, which is hooked onto the temperature controller, which would give me a very, very accurate change in temperature, to like grow or dissolve the compounds that I'm looking at. And I wanted to talk about some of my failed attempts because at first, when I started using the solutions that I was working on, it was basically a mix of or solvent of methanol and IPA, and because of that, I couldn't grow any decent-looking crystals. As you can see, you get these like straight lines of stuff, and we hypothesized, or Mike did, that it's probably they ran into some kind of solvent front, and so they can't grow anymore, so they turn, and then like they just don't form the crystal shapes that we would want it to. And afterwards, I grew everything in only IPA instead. So this is the powder form CHS that I had, that I looked at underneath the microscope. This is form 2 CHS, the seed crystals that I used to put into a solution that is saturated at 22 degrees Celsius. And after roughly 4 days, I grew some of like the nicer looking crystals that I would want to look at more. So with that, I want to show you guys some videos of crystals. Crap. Where's the, sorry. Okay, so this is probably just crystals growing together. Like, you will have the nice looking ones that I showed you at first, like the kind of kite shaped one, but then they're all like clumped together as they grow, so then it just looks like a bunch of stuff. But you can see them growing and getting bigger over the course of like 18 hours or 16 hours or so. And then I also wanted to show you guys that I was trying to grow this one that I thought was pretty nice looking, and it was getting bigger, and then yeah. And for some reason, even with the same solution at a different saturation that it was growing, they started growing these needle shape that I was growing yesterday. So it might be something that is actually, it's kind of like a question right now, but it's something that Mike and Zubin are working on for, for different saturation of the same compound, you can actually get different polymorphs. This is growing and just slowly. If I can fast forward it, you can see it. That. Okay. So with that, my conclusions are that I have these data that I got from my solubility experiments from form 2 of CHS, and also that the metastable zone width was too large to be taken into account for the polymorph transformation experiments that I was working on, and also that the growth and dissolution of CHS has been observed underneath the microscope, like I showed you guys. And I want to acknowledge my mentors, Mike and Zubin. They've been like my parents for the last 10 weeks. and my PI, Mike Doherty, and also UC Leeds people, Erica and Matt, and the folks back at Cal Nerds, Dan and Chris, and go Bears. I'm just kidding. Yep.